Hello everyone, welcome back. I want to move on to the new section, so 3.6. Just so you know, I pushed the homework, WebAssign homework, 3.5 and 3.6, so that's WebAssign number 9, I believe. It will be due Wednesday. There's a couple questions in that one that involve this distribution, this section 3.6 stuff. And I didn't want to force anyone to have to work on that over the weekend if they didn't want to. So it's now due Wednesday. So if you want to get it done 2 days early and still get that bit of bonus credit, as long as you do it by Monday, that's fine. Anyway, we want to talk about a new distribution. That's the Poisson distribution. And the Poisson distribution is a bit strange compared to our other discrete distributions, because so far our other discrete distributions had these distinct trials of some kind. So for binomial, geometric, negative binomial, we had independent trials, Bernoulli trials we called them, and they were happening one at a time. First trial, second trial, third trial. Did I get the thing or not? Did I get the thing or not? And then for hypergeometric, we were drawing cards or pulling a thing out of the bag or whatever kind of selection was going on. The Poisson distribution is quite a bit different. It's still a discrete distribution. My random variable is still going to take whole number values. However, what's happening is that we have some length of time or space, and what the Poisson distribution is going to count, it's going to count the number of times in this interval that some event occurs. So we have these random occurrences of some event. Lightning strikes, defective components on our assembly line, people coming into our store, something like this. And the important thing is that the length of time between any two occurrences is independent. So when the next one's going to happen doesn't depend on how long it's been since the previous one happens. We have this sort of true randomness going on here when these things happen. And so the information we do have is we have some average number of times. So average number, I'm clicking too much. Let me switch back to my regular handwriting. So the average number of times the thing occurs in, let's say, the interval, for meaning whatever interval of time or space, whatever the situation is. Maybe we're talking about this thing, how many times does it happen over the course of this year? So the average number of times, which is just going to be an expected value if we're counting how many times the things happen, is given. So the idea is we know on average how many times the thing tends to happen, and so we're going to measure, our experiment is we're going to look at, okay, this particular time interval, so maybe it's a year, this particular year, how many times does the thing happen? I know on average how many times it tends to happen, but my random variable is going to measure number of times the thing happens in this particular interval. So again, our setup is we have some period of time. We know on average how many times our thing or event occurs within that period of time. But we're going to look at one particular period of time, and my random variable is going to count how many times the thing happens. And the caveat is that we need independence between occurrences in the sense that how long it has been since the previous occurrence has no effect on when the next one occurs. So really all that's doing is, okay, once I fix my length of time or space and I have this thing that's randomly happening, as I'm moving forward in time, just because it hasn't been very long yet since the last one doesn't mean I'm more likely to happen now than maybe a little bit later. And that's a very important piece of when this thing applies. So now this is very useful, particularly for measuring probability of occurrences of rare events that happen over a period of time. How many times did someone get struck by lightning this year? Things like that. In the homework, I'll give you a very old-fashioned example. How many times does a soldier get kicked to death by a horse in the Prussian army? More on that later. Things like this. And so we have a formula, actually, that measures this. And so again, Poisson distribution. What are our formulas for this? Again, the average number of times the thing's going to happen is what's given to us. And the expected value is, of course, mu. So we're given the expected value. And now we have a formula for the probability function. The probability of getting whatever little x many occurrences is going to be mu to the x times e to the negative mu divided by x factorial. Now this is a bit of a strange formula, and a bit we'll see where it comes from, but it is what it is, and we'll practice plugging it into a calculator in just a second. And then another interesting bit is that our sigma squared, or our variance, happens to come out as mu as well, which is a little nice. So let's look at an example just of how we would use a calculator or something. So say we're given something where Poisson distribution is going to model it. How many times does such and such happen this year or today? And we're told that on average it should happen 5 times. And then I want to know what's the probability that it happens 7 times. Well, then I'm going to have 5, because that's my mu, to the power of 7. And then I'm going to have e to the minus mu. Look back at our formula there. So e to the minus 5, and then this is going to get divided by our x factorial. So 7 is our x here, so 7 factorial. And then I would just punch that into a calculator. So we're getting 5 to the 7 times. Now, there's an e to the x button in blue on the left over here. So if I hit second, then that button, I get e to the power, and now I want to put negative 5. Okay, so there's the top of my fraction, and I want to divide that by 7 factorial. So math factorial is over in the probability tab. So there it is. So divide that by 7 factorial, and then we get our answer. So my probability here came out as about 0.1044. So about 0.1044, or 10.44%. Okay, so there's another example that I want to give that's like from your WebAssign homework. So this is the last one from the WebAssign homework. So give me a second to just write that. Okay, so this is number 7 from the WebAssign homework. Your numbers in this problem may be different. Those are a bit randomized, as you probably know. And it asks us an interesting version of a Poisson distribution question. One that we would actually refer to as a Poisson process, but you don't really need to worry about what that means. It does have a bit of a twist to it because it's telling us a rate, sort of how often in terms of like a speed, like a rate, does this thing happen, rather than our expected number of times it's going to happen for whatever time interval we're actually interested in. So it says this article suggests a Poisson process, so we know we want to use Poisson distribution. Can be used to represent the occurrence of structural loads over time. Okay, these structural loads are a thing that's happening. And it says, suppose the mean time between, that is not the mu. It's not. That's actually how much time on average occurs between this event. So each time one of these things happens, I get one of those structural loads, it's saying the average number of time before it happens again. So it's giving me a rate. So the first part of the question, it's saying it happens at a rate of about once every 0.4 years. And so when I look at part A here, how many loads can be expected to occur during a 4-year period? Well, they're occurring at a rate of 1 every 0.4 years, and then that's happening for 4 years, and so that's 10. So on average, I expect 10 loads every 4-year period. So this 10 is going to be our mu. And now if I look at B, what is the probability more than 13 loads occur during the 4-year period? Well, this is now Poisson distribution with our mu being 10. And the probability that x comes out more than 13 is going to be 1 minus, because it's the opposite of x coming out less than or equal to 13. And so you're going to get 1 minus, and then we would have to add up the probability that I get 0, probability that I get 1, up to the probability that I get 13. Now this calculation is pretty tedious because for each of these I'm going to have to go in and say, okay, what's the probability I get 13 of them? That is my mu, which is 10 to the power of my x, so that would be 13 there, e to the minus the mu divided by the x factorial. And so I would have to plug this number in for my p of 13, and I would have to do the same calculation for each of those terms, and then do 1 minus what I get when I add them all up. So for that one, it may be a good idea to use a web browser, Wolfram, something like that. It asks us, how long should a time period be so that the probability of no loads occurring during that period is at most 0.2? So we want our probability of 0 occurrences, which according to our formula is going to be mu to the x, which here is 0, times e to the minus mu divided by x factorial, which is 0 factorial. Remember, 0 factorial equals 1. And then something to the 0 power is also equal to 1. And so what is actually just e to the minus mu, we want that to be at most 0.2. Okay, so now we want e to the minus mu to be less than or equal to 0.2. And now I need to solve that for the mu. What mu do we want? Because the length of time that we decide on decides what that mu is. So in order to cancel off an e to the power of something, I need to use a natural log. And so I would go over to our calculator and say, okay, if e to the negative mu is less than or equal to 0.2, that means minus mu would be less than or equal to, let's pull up a calculator. So we need natural log of 0.2, which is about minus 1.6. We need a little more decimal places, so let's do 0.944. 0.944. We'll keep a couple extra decimal places so that we're not rounding off too much till the end. Okay, so that means the mu we want needs to be less than or equal to 1.60944. Now, we were given a rate for how many times this thing occurs, and it occurs about once every 0.4 years. And so that times whatever length of time should equal this mu, 1.60944. So the length of time I want is just going to be 1.60944 times the 0.4, which comes out as about 1.60944 times 0.4. That's coming out as about 0.6438. Okay, so that was the tougher one on the homework, and if you can follow along with what I did here, then you should be fine working your way through that. Now that we've finished these examples, now that we've done examples and we know what the formulas are, I want to show y'all where do the Poisson formulas come from. So from here on, that's the question I want to answer. And for your sake, if you want to keep your sanity, you don't have to know this stuff. It's not going to be required. But I know for some of you, you like the abstract math like I do. So I want to say, where does these things come from and show you that. Okay, so we want to get formulas for, I have some fixed time interval, and we have some average number of times it happens given to us. And the idea is that I can approximate this distribution, this Poisson distribution that I have, by pretending I take my time interval and break it up into a bunch of pieces. Let's say n many. And then I can think of each of these. Does it occur or not? As a trial. So this is a binomial kind of thing. Now, this isn't a perfect approximation because, one, the Poisson distribution doesn't limit me from having two occurrences real close together, which approximating it with this binomial would, because we're just saying yes or no. Do I get one of the occurrences in that chunk of my time period or not? And then also, the Poisson distribution, it's possible I could have, say, an occurrence in every one of these, but then some more occurrences. There's an upper limit to how many successes I can have with a binomial distribution. The Poisson doesn't have that kind of limit. So it's not a perfect approximation, but the idea is, as I break this up into smaller and smaller pieces, the difference that makes becomes negligible. And so the idea is that as my n, how many pieces I break up my time interval into, gets more and more and more, those pieces get smaller and smaller and smaller, and it does get closer and closer to being the actual Poisson distribution. So that's what we're going to do. We're going to say, okay, I have whatever period of time or space, and then I have my mu, average number of times it happens, fixed always, and then I'm going to break that up into some number of pieces, let's say even size, in many pieces. And then I'm going to look at the binomial. With n trials, each with probability of success. Now, notice the average number of successes or occurrences that I should have over this whole time period should stay the same. It's our mu always. So when I break it up into this n many pieces, when I say when I look across all the n many pieces, my expected value for that binomial I want to keep the same. And the expected value for a binomial is np. So I want NP to equal mu, every one of these. And so I want my P to be mu over N. Mu over N. So my P is going to be mu over N. Now what does that binomial look like? So binomial says what? We take N choose X, and then I have my probability of success, my P, but our P is now mu over N to the power of how many successes, and then we have our Q, which is 1 minus mu over N to the power of how many failures, which would be N minus X. And so what we're actually looking for is my Poisson distribution should be the limit as I break it up into more and more pieces, so as n goes to infinity, of this thing up here. So let me grab that thing up there. So we want this limit. Okay, let's break it up and see what we can do with that. So my n choose x is going to become n factorial over x factorial n minus x factorial. My next piece there is going to become mu to the x over n to the x, right? I'm just multiplying these things. And then my last piece there, let's break this up. So I have this to the power of n minus x. That's going to be that thing. That's mu right there. To the power of n times that thing to the power of minus x. Okay, so now let's talk about what happens to these things in the limit. So, because we're looking at limit as n goes to infinity, this piece over here, well, my mu is fixed. My x is fixed because we're just looking at our p of x for some fixed x. So I have 1 minus something that, it's got an n on the bottom. As n gets big, that's going to disappear. So then I'm getting 1 to the power of whatever minus x is, would still be 1. So in the limit, that term's just going to go away. Now, let's leave this one for a little bit later and look at this stuff over here. I'm going to leave this mu to the x off to the side, and also this x factorial over here. So the mu to the x and x factorial, we're going to move out of the way. And let's say that this equals the limit as n goes to infinity of, now I've got the n factorial. I've still got this n minus x factorial down here. I've still got this n to the x on the bottom. And then I'm going to leave this mu to the x over x factorial. And then also this 1 minus mu over n to the n off to the side for now. And let's look at what happens with this thing. Okay, so let's look at this piece here. N factorial over n minus x factorial. So all the numbers from below the n minus x, actually one above n minus x, are going to get canceled off. So this is going to become n times n minus 1 times n minus 2 times on down until I get to just 1 above n minus x. Well, how many things is this? We'd have 1, 2, 3 on down, and notice that this number is 1 higher than what I'm subtracting there. So that means I have, if I'm subtracting x minus 1 there actually, that means 1 higher than that is x. So I have x many terms going on. And so this n to the power of x, I can just put one of those n's with each of these on down and have each of these over n. And so what that means is that n over n, that's just going to be 1 times, now I have n minus 1 over n times n minus 2 over n times on down to n minus x plus 1 over n. But notice, if n gets really big, n is going to infinity, remember? These numbers get closer and closer to 1. The bigger n is, the closer n minus these end up being proportionally to just n. So in the limit, these are all going to act like a bunch of 1s, times 1, times 1, times 1, on down. And so that tells us that if I go back up to the top here, this term going on right here actually just goes to 1. And so that leaves this piece here. So we have this whole thing is equaling the limit as n goes to infinity of, and we had mu to the x over x factorial, and then we had this 1 minus mu over n to the n. Now there's a couple ways we could think about this. Intuitively, if I wanted to relate this to something that you've seen before, you could think of this as 1 plus and then negative mu over n to the n. And this looks like compound interest, where minus mu here is our rate, where I'm compounding n many times. And if I compound n many times per year, this looks like compound interest. As I take n to infinity, I take in the limit, that would become continuously compounded interest, which becomes e to the power of the rate. But here our rate is minus mu. And then our time period is just one time period, so I wouldn't have those. So you could think of it that way. Alternatively, you could do a substitution and say, if I let, say, x be that negative m over n, then in particular I also have that n is negative mu over x, and we have that x is going to go to 0 as n gets bigger and bigger. So that means this would become the limit as of 1 plus x to the power of negative mu over x. And this is the limit as x goes to 0, which I could rearrange a bit and say that's the limit as x goes to 0 of 1 plus x to the 1 over x, all to the power of, but limits can pass into the exponents, so I would take this all to the power of minus mu. But this limit here is one definition of the number e. E is a weird number. It's 2.72 something. But it's one of those weird numbers like pi. It has a decimal that just goes on forever and never starts repeating. And one of the ways we can define it is actually this limit that we found. And so again, that just tells us this piece right here is e to the minus mu. And so I've got mu to the x over x factorial, and then also an e to the minus mu on the top. So we have mu to the x, e to the minus mu over x factorial. And there's our distribution function for the Poisson distribution. Now there's no need to derive expected value for Poisson distribution because that's what we're given at the beginning. However, I may want to try to derive the variance, and I could think of this as, well, if I set this up as the limit of all these binomials, well then my variance should also be the limit of all these binomials as variance, and our variance was, for each of those binomials, is that NPQ, but our P again is our P was mu over n, and our q is going to be 1 minus mu over n. And so now let's look at this limit. We'll do a little arranging here. Let's distribute this n right there. So those will cancel, and we're getting mu times 1 minus mu over n. But as n goes to infinity, this fraction here is disappearing to 0. And so this is just going to be mu times 1 or mu. So our variance comes out the same as the expected value, just like we saw in our formulas. Anyway, I just wanted to show you all that. Thank you very much. The next WebAssign homework again is due on Wednesday, so make sure you don't forget about that. See you next time.